Welcome, Algebra 1 to Lesson 70. Today we're going to talk about probability, and then we're going to talk about designated order. Probability it's fun, actually. Probability is when you throw a dice and you try to guess how many times it's going to land on one. Or you flip a coin and you decide how many opportunities you have to roll heads or flip heads. So it's included in games of chance. Think gambling, think Uno, think playing any kind of card game, any kind of opportunity to guess at something, or anywhere where there is some degree of uncertainty. Probability is one of the tools that mathematicians use to try to eliminate as much uncertainty as possible. So the study of probability is based on the study of outcomes that have an equal chance of occurring. So a fair coin should come up heads as often as it comes up tails if we flip it enough times. We will assume that our coins are fair, nothing's weighted or anything, and that a die, which is the singular of dice, just one six-sided dice, that has six faces, that the faces will come up evenly if we roll it enough times. We also assume that individual marbles have equal chances of being drawn from a bag or an urn or a box or a bowl. And it is customary to call activities such as flipping coins, rolling dice, blindly selecting cards from a deck, drawing marbles, experiments, and to call the individual results outcomes. We call the act of equal probability outcomes the sample space. So those are some terms that you need to know. So the first term is experiments. Experiments are the act of rolling, flipping, selecting, etc. Okay, and the outcomes are the results, what happened, right? And your sample space that is going to be the set, or the number of times that we do this, or the set of chances. Okay? So we define the probability of a particular event as the number of outcomes that satisfy the requirement divided by the total number of outcomes in the sample space. So the probability P of our event, right? That's our experiment. Let me write that in here. It's the probability of our experiment. The outcomes that equal our criteria divided by the total in the sample space. Okay, this is the formula we are going to use in order to determine the probability of something. The probability of this experiment is the outcomes that equal our criteria divided by the total number of outcomes in that sample space. Right? So why don't we try a probability problem? Write this down and then pause and write it down, and then go ahead and press play. I'm going to clear the page. So pause this to get all your notes in, and then let's do 70.1. So 70.1, I'm going to type this so you can read it for yourself. So give me just a moment to do that. All right, so here we have 70.1. A fair coin is tossed 3 times and comes up heads every time. what is the probability that on the next toss, that's our event or our experiment, it will come up heads. So we want it to be heads. And we have two options. We have tails or heads are our possible options, right? So the probability is going to equal, on the next one toss, heads is only one of the options below. So 1, and we have two options, two possible outcomes. So our probability that it will come up heads is 1 out of 2. It does not matter what happened before. A fair coin is tossed 3 times and comes up heads every time. That is totally, it's ancient history. It doesn't matter what it came up in the past. The experiment is the next toss, that it will come up heads. And we know that if a coin has 2 options, heads or tails. So 1 out of 2 is all we can expect. We have a 50% probability of getting heads. It doesn't matter what happened before. Every toss is a brand new toss. Okay? So let's look at another one. See, that's a lot easier than you thought it would be. Let's look at 70.2. And I'm going to type that one as well. All right, just give me a moment for that. All right, so here's our problem. We have 6 green marbles and 8 red marbles are placed in an urn. All right, so here's our urn. Okay. We have 6 green marbles. So 1, let me get the bigger thing here. 2, 3, 4, 5, 6, right? And we have 8 red. 1, 2, 3, 4, 5, 6, 7, 8. Now all the marbles are the same size, same shape. There's nothing that you can feel on them that will differentiate between their color. Okay? 1 marble is drawn and then dropped back in the, I should say urn, sorry. I misspelled it. Autocorrect changed it. Then a second marble is drawn and dropped back in the, and that should say urn as well. Autocorrect has not been doing me well tonight. Both of those marbles were red. If another marble is drawn, what is the probability that it will be red? Again, with the misspelling, Miss Tracy. Oh my goodness. So let's look at our probability. We have 6 green, right? So let's do 6G. And we have 8 red. Let's do 8R. Okay, so our total number of marbles in the whole thing is 14 marbles, right? So our chances of getting a red marble is going to be 8 out of 14. So the probability of red, we have 8 red, so 8, and the total number of marbles is 14. All right, we can reduce, whenever you can reduce a fraction, we reduce a fraction, so it's going to be 4/7. And that is our answer. So the probability that would be red is 8 marbles out of 14. We could draw any one of those 8 out of the 14 and we'll get a red one. So 8/14 reduces to 4/7, and this is our answer. Easy peasy. It does not matter that this happened. All of this is in the past. It has no impact on what's going on right now in this turn. If we were to take the marbles out and keep them out, then that could impact, because the number of marbles in the urn would change. But right now, we're just dropping them back in the urn, right? So it doesn't matter what it was before. We're worried about this one time right now and what that probability is going to be. All right, so let's look at another one. I'm going to clear the page. And we're going to do 70.3. All right, and I am going to pause this and type in my problem so you can read it. All right, so here's our problem. A single die is rolled 3 times. The results are 1, 4, and 3 in that order. Okay, we've already established we don't care. We don't care what happened in the past. It does not matter what happened before. What is the probability that the next roll, that's all we're worried about, is the next roll, will produce a number greater than 2. So the probability that the next roll will be greater than 2, that's how we would write that, would be, sometimes it helps to make a sketch of what you're doing. So let's make a sketch of our possibilities. We have one side of the dice is a 1, one side is a 2, one side is a 3, one side is a 4, one side is a 5, and one side is a 6. Okay? So what we have to do is we have to put the total number of outcomes on the bottom. We have 1, 2, 3, 4, 5, 6 possible outcomes. So that's our total outcomes. And greater than 2 is the experiment. That's the event that we're looking for. So greater than 2, we have 1, 2, 3, 4 possible outcomes that could be greater than 2. So we have 4 out of 6. Those are both even, so we can reduce that to 2 out of 3. And that is our probability that we'll roll something greater than 2. 2 out of 3. And that is the answer to 70.3. All right, so write that down. Pause, write it down. I'm going to clear the page. And let's do 70.4. All right, I'm going to type it again. All right, so here's our problem. 2 dice are rolled. So we have 2 dice now. What is the probability that the sum of the numbers rolled is a 7 or a number greater than 8? So we have 2 probabilities here that we need to work out. So first of all, let's draw a diagram of those combinations. So we have 2 dice, right? The 1 dice, I'm just going to draw a little grid here. The possibilities for the 1 dice is 1, 2, 3, 4, 5, and 6. Those are the opportunities for the first dice. Now, we have the opportunity to pair it with the second dice because it says 2 dice are rolled. So if the first dice lands on one of these and the second dice lands on a 1, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. And 1 plus 6 is 7. Okay? If the second dice lands on a 2, 2 plus 1 is 3. Then that would be 4, 5. 4 and 2 is 6. 5 and 2 is 7. 6 and 2 is 8. Okay? If the second dice rolls on a 3, then it'd be, and let me make this clear, this is the second dice. And this is the first dice, okay? So if the second dice lands on, all right, 3 and 1 is 4, 3 and 2 is 5, 3 and 3 is 6, 3 and 4 is 7, then you have 8, and then you have 9. If the second one lands on a 4, then this would be 5, 6, 7, 8, 9, and 10. If it lands on 5, we would have 6, 7, 8, 9, 10, and 11. And if it lands on a 6, we would have a 7, an 8, a 9, a 10, an 11, and a 12. All right, so here is our sketch of what could happen, right? And let me draw this little line here so we can keep them straight, so we can see them better. Make sure we got them on the right row. All right, so what is the probability? All right, here's the probability. The probability of A, that it lands on a 7. So first we have to calculate what are our total possible outcomes. So we have 6 by 6. So 6 times 6 is 36. We have 36 outcomes. And if you, if you don't believe me, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36 possible outcomes. Okay? Now, we need to know the number of times that those 2 dice rolled are going to equal 7 in the whole range of outcomes. So we look for the number 7. All right, so there's 1, there's 2, there's 3, there's 4, there's 5, and then there's 6. So there are 6 possible ways for it to roll and get a 7. So we put 6 over 36 here. And we can reduce that to 1 over 6. So that is the probability that we could roll 2 dice totaling 7. 1 out of 6. Okay? Or 1/6. So now we have to look at the probability for B that it will be a number greater than 8. So our event is going to be greater than 8. So again, we have 36 possible outcomes because we've already determined that. And now we have to look at the results that are greater than 8. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes that are more than 8. So 10 over 36, we can reduce that. Divide both of those by 2, we get 5. 36 divided by 2 is 18. So we get 5 over 18 is the probability that we can roll something greater than 8 with 2 dice. These are, these are actually kind of fun because you kind of get to make little sketches and draw here and there. So anyway, that's how we solve probability. The total number of outcomes is the denominator, and the total that we will get what we're looking for, that the total number of chances that will equal our criteria, goes in the numerator. And then we just reduce the fraction if we can. And then right here, we're just giving it a name. Remember, kind of like functions, we had f of x, g of x. This is p of x here. The probability of x, and x is our event. And we are just giving that event a name. In this case, the name is that it would equal 7, and in this case, the event, or x, would be that it was greater than 8. So that kind of makes sense a little bit when you look at it like that. All right, so let's move on to designated order. If you need to write this down, do so. I'm going to clear the page. All right, so designated order. The probability of future outcomes of independent events happening in a designated order is the product of probabilities of individual outcomes. For example, if we toss a coin, the probability of getting a heads on the first one, tails on the second one, is 1/4. And here's how we do that. We put the probability, so we have a coin. So our possible outcomes for the coin are, Actually, I should probably draw a circle. Our coin outcomes are heads or tails, right? So what we're looking for is the probability that we will get a heads on the first one and a tails on the second one. So how do we do that? We have two sequential events here in order. We're looking for a specific order. So here's what we do. We first put the probability for heads, 1 out of 2, because that's 1 out of the 2. And then we multiply it times the probability for the second turn. And tails is 1 out of 2, so 1 out of 2. So that comes out to 1 times 1 is 1, and 2 times 2 is 4. So the probability that we will flip a coin and get a heads first and a tails second is 1 out of 4 chances. Right? You see how that works? All right, so let's try it with a sketch. Here's how we would sketch that out. So on our first toss, we could either get a heads or we could get a tails, right? On our second toss, we'll either get a heads or we'll get a tails. Now, if we're starting back with getting the tails and we flip it again, we'll either get a heads or we'll get a tails. What we're looking for is heads, tails, right? Heads first, tails second. We have 1, 2, 3, 4 possible outcomes. 1 out of 4. Right? So one pathway that matches up out of 4 total pathways that could happen. You could feel free to draw a sketch like that. If that's what works for your head, this is faster. And it will give you the exact same answer. All right, so let's try an example problem for designated order. All right, this is 70.5. I'm going to pause and type the problem. All right, so this is a designated order for another coin toss, and it's going to be tossed 4 times. What's the probability that the first 2 times it comes up heads and the last 2 times it comes up tails? So let's set up our problem. So our probability is that we want the first 2 times to be heads. So heads, heads, and the last 2 times tails. Tails, tails, right? Remember, our coin only has heads or tails. These are our outcomes. These are our total outcomes, right? So let's solve this. I'm going to let you solve this, actually. So pause the video and solve this designated probability order and let me know what you come up with. And when you're done, press play and you can see the answer. All right, if you got that a probability for heads, heads, tails, tails is 1 out of 16, then you are correct. So what we did was we looked at the pattern that we wanted, and for heads, we wrote the probability, 1 out of 2. We have 2 outcomes, and we wanted this 1 out of the 2. So 1 out of 2 for heads, and then we had 1 out of 2 for heads again. And then for our tails, we had 1 out of 2, and tails again, 1 out of 2. And then we just multiplied straight across, and that's 2 times 2 is 4, times 2 is 8, times 2 is 16. So 1 out of 16 is the probability that we come up with heads, heads, tails, tails when we flip a coin. All right, we have just one more, and I'm going to clear the page, and I'm going to let you, well, we can all solve it. It's a little bit different. All right, so if you haven't written this down, pause and do so. I'm clearing the page now. All right, 70.6 All right, let me pause and type this up here. All right, we have 70.6. The spinner shown is spun twice. What is the probability that the spinner stops on 4 and then 3? So here's our probability. We have 4 and then 3, right? Now, first of all, let's look at the total number of outcomes. So our outcomes, the spinner could land on is 1, 2, 3, and 4. So that equals 4 possible outcomes. So we put that on the bottom. First of all, for it to roll 4, that's 1 out of 4, right? 4 is only in here one time. And now to roll the 3, there's only 1 3, right? So that's still 1 out of 4 possible outcomes. So we multiply that together. Sorry, that goes up there. So we multiply and we get 1 and 4 times 4 is 16. So our possible, or our probability that we'll roll a 4, or sorry, not roll, spin a 4 and then spin a 3 is 1 out of 16. Okay, and if you wanted to draw a designated order for that, we could do that. We could just do the 1, 2, 3, and 4, okay? And the probability for each one of these would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And what we want is for it to roll the 4 first and then the 3. Okay? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And it's this 1 out of the total 16 that we want, because we want it to roll the 4 first and then the 3. So you see, this is so much easier, but it does the same thing that this does. All right, that is all we have for lesson 60. Please be sure to take good notes because you're going to see this again. It's kind of fun. I enjoy doing these, and I hope you like them too. They're a little challenging, and they're just not super complicated or super hard. It just requires a little bit of thought and real-world application. All right, I will see you guys in lesson 71.